Hello everyone, welcome back to my channel. Today let's go over a medium level question that I just solved on my own. So I'm super happy about this and I'm very glad that I was able to come up with my own solution to this question without any help. So let's go over it and let me show you how I did it. So this is question 2096, step-by-step directions from a binary tree node to another. So you're given this tree node class, this object, basically. It's a standard tree where you have not only binary searchable values, but you have a left and a right child. So it's just a standard tree. And then you want to find the path to go from the shortest path from the start to the end. And also all the values are unique. So that's making our life a little easier. So let's first understand that we can also go up and then also down. So let's go ahead and first build the tree. Let's make a default dict of type list. Basically, we want to extract for each node. If it has a left child, we can go down. That left child can also go up. That node has a right child, we can go right. That right child can also go up. So let's record not only the node value that we're going to go towards, but also the direction. So let's go and do a BFS level order traversal. So let's go ahead and just explore row by row, left to right. So let's call this the current node, and let's pop left from the queue, first in, first out. If the current is not null, so nodes can be null, and if current has a left child, then we're going to append using the current's value as the key. We can say that we want to go left to the current.left.value with the direction. Cool. If also we can do the same, saying that we can go to the current node up from that left node. And let's do the same thing for right. Again, from the right child, we can go up as well. Cool. And then, again, if the node is not none, then it might have children. So let's go ahead and append current's left child and current's right child, those tree node objects, each with 3 attributes. And now let's print our dictionary just to verify that we've done this correctly. Okay, so you can see from 5 you can visit 1 and 2. From 2 you can visit 5. From 2 you can visit 5 going up, left 6, right 4. Cool. So now to find the shortest path from the start to the end, knowing these are going to be unique node values, let's run a Dijkstra's algorithm and let's keep track of the number of sort of edges or expansions, basically exploring how many layers we can visit. And let's also keep track of the node value, which we're going to start at the start value. That's an integer. And then also let's do just a dummy direction x, because we're always going to need the direction to keep track of the path. But for the first one, obviously that doesn't matter. And then let's keep track of the total path that we take, excluding the current value, because there's no direction to get to the root node. It's just, or the start node, because that's where we're starting from. And then let's run a Dijkstra's. Let's make a scene to avoid infinite loops. And let's call this the hops. And then let's call this the node. And then the directions. And we're going to heap pop from our queue, sorting by this as the smallest value, because this is going to be a greedy way and it's Dijkstra's. So if the node is in our scene, if node of 0, which is just the value itself, the integer, is in scene, then we continue. Otherwise, we can add node of 0. And again, we're going to try to explore the neighbors of self.d node of 0, because the keys to this dictionary are only those, only the integers. And then we can push onto our queue hops plus 1, because we're exploring a new layer, right? An edge or a layer. And also we're going to have the neighbor itself, which is a combination of the value and then the actual direction we care about. And then we're also going to add to directions neighbor of 1, which is just going to be that string that we have. And at any point, if the node of 0 is equal to the destination value, let's print directions. And we know that's going to be the best answer because we're doing this in a greedy fashion. Let's see what's going on. So this is fine. Perhaps we don't need this. So just 3 parameters. Let's try. So we have a bracket there. We need that there. And looks like we can try it again. And let's get rid of this bracket. Was never closed. So let's call this first. Second, third is. Oh, we're pushing onto the queue. Hops plus 1. This is not supposed to be along with the neighbor. I think that was the problem. Let's do this. These parentheses can get a little bit annoying at times. Let's just do this. So the first value is the new layer. So we're incrementing the count, the neighbor, directions plus neighbor of 1, which is just, this is a string concatenation. So let's push onto queue first, second, third. And now let's try it again. Okay, perfect. So you can see up, up, right, left, because we're doing this greedily and we're trying to get to the destination value in the shortest path. And then once we have a directions, we can just return it, right? Okay, let's run this. Submit it. And there you go. Passes all test cases. So again, I'm super happy that I was able to come up with my own solution to this question without any assistance and solve it completely on my own. So that's it for this video, and thank you for watching.